Hello, everybody. Welcome to the 10 Days of AI Basics. This is Harper Carroll, and today we are on day 4 where we're talking about model training. So if you don't know me, I am Harper Carroll. This is Harper Carroll AI. Check out my page for a quick intro about me, get to know my background in AI. I have about 10 years of experience, master's, undergrad degree, etc. And definitely check out the first 3 days. This is meant to be learned in a series. So I have 10 about 90-second shorts, or I guess there are 60-second shorts on YouTube, 90-second shorts on Instagram, and about, right now we're on day 4 of the longer form versions of each of those 10 short days. So again, today we're on model training. So quickly recap of what happened last time. We talked about model architecture, we talked about neural network architecture, layers, activation functions, neurons, etc. I was also just on a podcast about the neural networks explained, and we went over very similar topics. However, the 10 Days of AI Basics model architecture video, we go way more into depth on the types of model layers there are, etc. So there's that, but you can also check out the podcast. It's a really fun conversation with my friend Naz, who is now my friend after the podcast. So check it out. I will link that here, and excited for you to see it. So let's get started on model training. There is a lot of things to talk about here. And training, again, is the heart of machine learning. It's basically where the model learns from the data it's been given. So if we recap the days 1 through 3, we talked about what is AI and what's the difference between AI and machine learning. Then we went into data, and then we went into model architecture. And so what training does is it combines data and model architecture to make a model that actually does something. So we have the raw skeleton of the model from the model architecture, but then we have to feed it the data so that the model can flesh out this skeleton, update its internal parameters, and do what it needs to do, properly transform the data using the model architecture, update its internal parameters so that it can appropriately apply functions on the internal input data to create the output data. So what model training does is it fleshes and molds this model architecture to create a series of functions. So again, we have these variables that we have in this model. If you remember from math, or if you have a math background, we basically have these variables, and we want to see what values do we need to assign to each of these variables so that the input is transformed into the output. And that's what training does, is it uses something called gradient descent, where it goes back and it updates its internal parameters to update these variables to create the appropriate series of functions. And so again, what models do is they basically do a series of matrix multiplications on the input as it comes in. So we have input data coming into the model, going through a series of matrix multiplications, and then transforming into the appropriate output. What training does, again, is it takes this input data, figures out what those matrix multiplications need to be to then get the appropriate output. So this is really interesting. And then again, once you're done with training, then you have deployment, where if you're using a model like ChatGPT, you're no longer learning what the internal parameters are, usually. But you're no longer learning what the internal parameters are. You have set those from the model training phase, and then it uses those to then apply those functions. So rather than having the input and the output, and you learn the body in between, you morph the body so that the input is appropriately morphed into the output. You have the input and the body to then create a new output. You're not sure what it is, but you're hoping that it performs well on that. So I hope that makes sense. So again, in training, you have the input and output, but in deployment, you have the input and the body, the model architecture that has been trained on the data. So that's the kind of finished model that you are deploying. And we will talk about deployment on day 9. So what model training is it's an iterative process, and it is the process of iteratively improving the model's parameters, as we said, to appropriately create functions that transform the input into the output. So let's look at an example. So say we want to train a model to classify as a dog, a cat, or a duck. So we have an image, we pass it through the model, and we say, is this a dog? Is this a cat? Or is this a duck? And we are basically, at the beginning, we have this raw skeleton of a model. And let's just assume at the beginning, it's just random. So at every step, it just guesses dog, cat, duck, just like equally. So we would expect its accuracy, so the percentage of ones it gets right, to be about 33%, 1 in 3, if it's randomly guessing. In the same way, if you're randomly guessing something with 2 classes, you'll probably get it right on about 50% of the time. So if you're flipping a coin and you guess heads every time, you'll probably get heads about 50% of the time. There's no like methodology for what you're doing. You're just randomly guessing. So in this case, there's 3, so it's about 33%, 1 in 3, rather than 1 in 2. And what you're doing is you are showing the model an image, it guesses, and then it learns, is this a dog, a cat, or a duck? Imagine for a second that this is a person. So, or a little person, like a baby, and we're training a baby how to look at a picture and say, is this a dog, a cat, or a duck? So if we give the image to the child, again, they'll just randomly guess. They've learned the 3 words, they're just guessing, they have no idea. Then, over time, as it's guessing and it gets the feedback, so say it guessed it was a cat, but then it learns, no, that was actually a dog. Or it guesses it was a duck and it says, no, it was actually a cat. And it guesses it was a cat, yes, that was a cat. So over time, the child starts to learn what features make this a cat? What features make this a duck? What features make it a dog? What features make it not a duck? What features make it not a cat? And so it learns in its mind this internal representation of ways to identify which is which. And that's what a model is doing as well. So it is updating these internal parameters, and you can kind of think of these internal parameters as, a lot of neuroscientists will disagree with me on this, but they're like neurons. And this is what we do when we talk about model architecture in day 1 is like, the models are made of neurons. Neural networks are made of neurons that learn information. And again, the neurons are connected to each other as the model,
data,
is propagated from left to right. So it goes through layer. Each of those layers are made up of neurons. So again, watch day 3 if you haven't yet, because it's important information. Those neurons start to represent data, information. And the layers do as well. So, one layer might learn, what's the outline of the head? Is it, does it have pointy ears? If so, it's not a duck. It might be a dog. Could definitely be a cat. And again, it is learning these features over time. And what those features do is, or how they're represented, they are layers within the model. They are the numbers that the model starts to learn. So I know it's kind of confusing thinking of these things as numbers, but you can one thing I learned when I was younger, I interned for this Columbia Business School professor when I was going into my senior year of high school. And I studied social and economic networks. And when I was going in to meet with him, I thought math was cool and I liked to, do applied math, to get input, make an output. But when I was working with this professor, Kostis Makleras, I learned that you could actually use numbers to model any social situation. So you could literally represent people's opinions about things as numbers. And you could find that, having a really diverse set of opinions, if you iterate and share the information over time, you can then converge to the optimal opinion mathematically. So what that means is basically diversity is actually mathematically optimal to converge on the correct result. So you don't really need to think too hard about that. But what I'm trying to get at is that you can model pretty much anything as numbers. Social situations, ideas, images themselves are naturally numbers. We talk about that in day 3. And so that's what you're doing when you're updating these internal parameters and you're creating these functions, is you're able to actually model those ideas as numbers, and then you're able to apply functions because you're modeling them as numbers. And so I hope that's clear. If you have any questions about that, you can leave a comment below. But yeah, so that's kind of what you're doing, is when you're training the model, you are finding numbers that represent concepts and features and ideas just using math. And so that's what I thought was really cool going into my senior year, and that is part of why I decided to study math. I've always loved math, but I thought that was really cool, and little did I know that was actually machine learning. So I ended up finding machine learning in school and was like, oh wow, those are like the same. I didn't know I was doing machine learning when I was studying social and economic networks, but I was. Some of the key aspects of training are that it is iterative. So it goes through a bunch of samples, it learns from them, and then it updates its parameters, and it does it again and again and again. It's data-driven. So again, these parameter updates are based on the data that it's learning from. And it's goal-oriented. So either it's classification or it's prediction of housing prices, or, we talk about that again in the earlier days of the 10 days of AI basics. We talk about the different types of questions that you're answering. But again, so you choose the goal and then you are training for that goal. And so in the case of the dog, cat, and duck, that is a goal. It's a classification problem from an image into one of 3 images. So our ultimate goal of model training is to find the sweet spot. So the parameters that make the model perform best across the broadest array of data. And what I mean by that is we're not only minimizing the errors on scene data, so data that causes the model to update its parameters, data that the model learns from, but then also new data. When we're testing the model, how does the model do? So we have the idea of different sets of data. We have the training data, we have the validation data, and we have the test data. And the training data is used to, again, train the model, to update the model's parameters in its architecture. It gets the input, it gets the output, and then it passes it through to update its parameters. Validation data is to test periodically through the training process to see how the model is doing. So those outputs, those results from the training data, are not used to update the model's parameters. They're just used to gauge how's the model doing. Is it getting better at classifying dog, cat, or duck? Is it getting worse? And then we have the test data. And the test data is held out until the model is done training, and then you're able to see how the model does on data that it, didn't look at before at all. And so that's how you're able to tell that's how you gauge the model's accuracy in the end. So model accuracy is something we will discuss, but it is the percentage of questions gotten right or wrong on the test data. And so that measures how well a model is doing. We will talk about different measures of model performance in upcoming videos. Accuracy is just one of them. But basically, at the end, you use the test data to get a metric of the model's performance. So you're not testing the model on data that it's seen before because it's learned from that. So that doesn't count. You can't train on your test data because then you don't actually know how the model is going to do when it goes out into the world and it sees data that it's never seen before. I'm going to talk briefly about the parameter space. It is the multidimensional space of all possible parameter values. So if you have, a model that has 3 billion parameters, each of those parameters has, possible values that it could have. And so the total of all possible values for all of those parameters is the parameter space. And imagine it as this space that exists, that it's super high dimensional. We can't really even fathom it. There's a point in this parameter space with the lowest overall error rate on all data coming in and coming out. And what models do is they try to iteratively find that point. And how you do that is by finding minima over time. So what you want to do every time the model is learning something is you want to move closer and closer to that optimal point where the model does the best. So again, this point represents the values for all of the possible parameters. Imagine that you're in 2D space, longitude and a latitude. You can classify yourself in one point in this 2D space, longitudinal and latitude space on a flat Earth model. You're in one point, but that one point contains values for both longitude and latitude. So in the same way, the optimal point is just one point, but it contains values for all of the parameters. So all of the parameters have a value to find that one point. In the same way, where you are is just one place in time, one point in time, but you have a longitude in space, but you have a longitude and a latitude. So both of those variables in 2D space are covered in this one point. So what loss functions do is they aim to get you closer and closer and closer to that optimal point. The role of the loss function is to measure how well or how poorly a model is performing. And so it measures the difference between the answer that it got versus what it should have gotten. And minimizing the loss function is the main objective during training. So we talked about the goal. The goal is really to minimize the loss function. So you want to define your loss function when you are training a model, because that is the goal, to minimize that. And so what gradient descent does is it finds the direction that, this point in space needs to move to step towards that point that is the optimal lowest value. And the way it does that is complicated. And I actually would like to have a separate video on gradient descent. It's super cool, but it's actually worth just making a video on because this video is going to be super long already. But gradient descent is really cool. But what it does is it finds the gradient, which we will talk about, and it moves in the opposite direction. So it's moving downhill towards the direction of less error. So imagine the hill increasing is more error. It's moving in the direction of less error. And I know that's confusing, so we need a separate topic for that. But what gradient descent does is it makes the point step in the direction of less error. And so you get a new point. So, I take a step north, and so I have a new point with different longitudinal values, but my latitude value stays the same because I stepped north. I have a new point, but again, that covers both of those points. So my internal parameters of longitude and latitude have been updated. Hopefully that makes sense. So I will make a separate video on optimization algorithms, including gradient descent, etc. There's something called overfitting that I would like to discuss here. So overfitting is when you have the model be too good at its training data so that it actually doesn't generalize well. So what that means is you have the model doing really well on the data that it learns from, so the training data, but then when you go to look at validation data, the data that it hasn't learned from, it's not doing very well. And so what that means is that the model is probably not going to do well on data when it leaves the training phase. And so that means it's not generalizing well. And generalizing is when the model is able to do well on data that it hasn't seen before. You can think of overfitting as like memorizing the training data as opposed to learning general patterns. So one example of overfitting is, say we are classifying dog, cat, and duck, and we actually have in all our examples the noise that the animal makes. So it's like an image of the cat, and then it has like a little bubble, and it says like meow, and the dog it says woof, and duck it says quack. And when we go out into the world, we see that it's actually not performing well anymore. It did really well on our training data, but out in the world, it's like making a lot of mistakes. So the accuracy when we're measuring on the training data is really high, but when we go out into the world, it's not as high. And we end up finding that it relied so heavily on this value of the sound that out in the world, it's not always getting that sound in the image of the cat or the dog. It's not always seeing meow. So it has overfit on the training data. And what we want to do is find ways for regularization. And regularization is a way to generalize the model so that it is less likely to overfit on training data and perform better on unseen data. So either the validation data or the test data. So some examples of ways we can regularize are dropout. So dropout are when we randomly drop out neurons. And what that does, and as we talked about in the day 3 in model architecture, is dropout basically makes you rely less heavily on any single neuron because you're just randomly dropping out neurons. So say you hit a layer, you're passing through the model and it hits a layer where 50% of the neurons suddenly become 0. They're suddenly just gone, basically. What you have to do is distribute your learnings across other things. You have to say like, oh wow, so the neuron that tells me to look at the sound is suddenly gone. So now I have to start looking at other things. Maybe it's the ears. And so you are less reliant on any single neuron and, as a broader analogy, like feature. Dropout is only active during training and not during inference. What that means, again, inference is when you are running the model out in the world. It's been deployed, it's ready to go, it's no longer training. That is inference. And then versus training, which is when it is updating the parameters. It is training. At inference, dropout is no longer used. So you can kind of see all the neurons. Another thing you can do to help with regularization is early stopping. So one of the reasons we use a validation data set is that you can see the difference in performance, accuracy in today's example of performance. You can see the accuracy between the training data and the validation data. And if that delta, if the difference between the two of those starts to get bigger and bigger in the sense that the training data is performing really, really, really well, and the validation data is performing less and less and less well, you know that it's overfitting because it is relying so heavily on the data set that it's seen that it is starting to find features in there that are actually not really generalizable to new unseen data. So it's not good. It's time to stop. And you find this spot where it's a sweet spot. So you're tracking versions of models. So this version of the model has these parameters and it gets this value on training accuracy and this value on validation accuracy. That was training iteration 100. Now this is training iteration 500. It has this accuracy value for training and this accuracy value for validation. Then you want to stop at that version. So again, validation is like every set number of training updates to the model's parameters, you test on a held out validation set. And then you can choose to find the version of the model based on, how far it is into its training iterations and how many updates it's made. And you find that version with those specific set of parameters, as in with that specific point on the map where each of those parameters has a value to represent a single point in the loss curve that is the best on both training and validation data. So that is an example of early stopping, where you don't train, say you want to train for 10,000 iterations. You actually decide to stop at 4,000 because you find that after 4,000 iterations, the model's validation data accuracy starts to go really down and the training accuracy goes up, showing overfitting. So instead, you stop at 4,000. You're also saving compute because past 4,000, you'll just overfit more and more and more, and the model will perform more and more poorly on held out training sets. So you're saving compute and you're finding a model that actually works better. So we talked about overfitting, and I actually just want to briefly touch on underfitting, and that's just when the model is just like not doing well. It has low training accuracy, low validation and test accuracy, and the model is just perhaps too simple to capture some of the underlying patterns. So some ways to mitigate that are to increase the model complexity. So add layers, add neurons, which again would increase compute requirements, maybe make it more expensive, take longer to train, hard to access that kind of compute, etc. But you might need that. You could also try reducing regularization. So if you have dropout, L1 or L2 regularization, then just remove that. You could also try just training for more epochs. So go through, and again, we'll talk about training processes in the next video, but epochs are a full pass through the entire data set. So you could just try doing training again, just moving through that same data set over and over and over again for more epochs. These days, people tend to just use one epoch, which is something I saw a little while ago. I don't know if that's still true, but that's what I saw then. But you might just try increasing the number of epochs. So I remember seeing something that was like for models in other languages, besides English, you might just need to increase the number of training epochs so that the model just continues to like see the same data, but learn from it over and over again to update its parameters. And they found that increasing the number of training epochs drastically increased the model's performance on, languages with less data. So they couldn't really increase the data that they had. They were able to just train for more epochs, and it did a lot better. Data augmentation is, we talked about this also in the 10 Days of AI Basics, where you just change in day 3, where you just change the data that you have and like rotate it or whatever, change the coloring to make your model then have more data. And this also implies that just getting more data in general can handle overfitting, handle improved generalization of the model. Another thing you need to be concerned about with model training is class imbalances. So for example, say I have 90% cats and 5% ducks and 5% dogs. And I train the model and I'm like, wow, it gets 90% right. And I find that actually it's just guessing cat on every single example. And when it goes out into the world, it does horribly because the data is actually more evenly distributed than that. Or even if the data isn't evenly distributed out in the real world, you still want it to not just like guess based on what it's more likely to be. You want it to actually find the features and guess based on that, not just like probability. Sampling techniques are a way of helping to mitigate class imbalances in your data. Oversampling is when you increase the number of samples in the minority class. So for example, you can do data augmentation techniques on just those. So if we have, again, 5% dogs and 5% ducks, we just like create a lot more images of the ducks and the dogs, just like rotate it or change the color or whatever or shift it. We manipulate that data to make more of it. Undersampling is when you decrease the number of samples in the majority class. So instead, we just cut off most of the cats to make them evenly distributed. We just get rid of most of our samples. One of the issues with oversampling is that it can lead to overfitting, especially if you're just like replicating the data or transforming it. It's still just like learning on those pieces of data rather than having a lot of data to learn from. So again, it can lead to overfitting because it's just like studying those few pieces of data so well that it might start to learn, the speck in the back of this, there's 5 dog images and 2 of them have like a red speck in the back. And I think that red speck means that it's a dog because there's so many, you're duplicating that so many times that 50 samples with a red speck in the back are dogs and the other samples don't have that. And so you're starting to just analyze these small images so much, these few images so much, that you are learning features that are actually not relevant to whether it is a dog. But it is in the data, but it's not in the real world. Undersampling is an issue because you might lose important data from the majority class. So if we're cutting out most of the samples of the cats, we're losing a lot of data in those images. And we want the data. Data is good. So it's a shame to just get rid of it. There is a type of synthetic data creation. So it's called synthetic minority oversampling technique, SMOTE, which is when you can create synthetic data from the minority classes. So it's like learning new features from the synthetic data. It's not just like the same feature, the same data replicated or transformed or whatever. So transfer learning is something that I want to cover that is really important. And you'll see today that most models are not trained from scratch. So the concept of training from scratch is like training from randomly initiated values. So remember, we have the input, we have the output, and then we have the parameters in the body of the model that we're then updating to make sure that the input is then transformed into the output. Again, we have these variables that are then iteratively updated to make these functions that transform. Randomly starting would be randomly setting these values. And what that looks like is, as we said in the beginning, with like randomly guessing cat, dog, duck, and getting like a 33% score at the beginning, just randomly guessing across the classes. This requires an extraordinary amount of compute. That is because you have to update all of the billions of parameters over and over and over again to get from like nothing, like static. Like imagine your concept of like what makes a person is, the face and the eyes and the mouth and the ears and like all these things. Like when you look at a person, you see the outlines of these things. Those are the eyes, those are the ears, imagine if it was just static. You just like looked at a person, there was just nothing defining about them. You basically just saw static. That is what randomly initiating a model does. And so to learn these features from like static, from nothing, is like, takes so much compute. It's unbelievable. Depending on how many parameters there are, which these days, right, we're training on billions and billions of parameters. So transfer learning is a way of standing on the shoulders of the work that has been done before us and learning from prior models. So for example, if you are classifying, different types of dogs, I won't do the cat, dog, duck one because there are so many models that exist already that classify animals. So that's just like, silly. But imagine you're classifying different species of dogs. You might start with a model that classifies animals, or a model that is just able to classify different things like animal or person or whatever. So it has learned from static to features, eyes and shape of the head and shape of the body. It has learned features already. And so then you're able to just get even more features. You're fine-tuning the model to learn, this is what makes a Bichon Frise from a Chihuahua. Like you're just fine-tuning the brain's feature detection of the model to be for a new task, certain types of dogs. And so that's much less compute than starting from nothing, starting from static. So I hope that makes sense, and that is what transfer learning is. Fine-tuning, I use that term, is when you take a model that is pre-trained, so like transfer learning, you take this model that has been pre-trained and you add your data to fine-tune the model's brain on those features. That is what fine-tuning is. So it is less data intensive. I mean, these days, again, pretty much everything is like fine-tuning because we don't start from nothing. So it's kind of just now used interchangeably with training because everyone kind of starts with a model that existed before. So for example, for a large language model, you might fine-tune Mistral. I have a bunch of guides out on how to fine-tune Mistral, which is a large language model that is really cutting edge and open source, so available to look at the different parts of the model and update them yourself if you have the compute for it. We can fine-tune Mistral on our own data. I have a guide on that, and I'll be making more as well on this channel. Yeah, so that is an example of fine-tuning a model. You're taking this model that has learned most of the features, and we're transfer learning by taking that model, and because it's open source, we are then able to pass through our own data and train it on our own and have it update those parameters to work well. So what I was able to do was take a model like Mistral that, just has its own distribution of words and how it outputs, to fine tune on my journal entries. So I was able to make the model speak like me in my journal. So it would like talk about people in my life, or it would write a random poem. And it was really funny and really cool and talked exactly like me. And it was kind of like a mirror looking at myself. So that was amazing and just a really cool thing to do. And it didn't take that much compute. It wasn't that expensive. And I only had 200 samples. Again, so not only is it less expensive to fine tune, but you also might not need many samples depending on what you're doing. I only had 200 samples and I trained it for like 30 minutes. So it cost me $1 to train a model to speak just like me. Amazing. And that is because of transfer learning. So when we're talking about models, we need to talk about some of the practical considerations like hardware. So you might have heard of GPUs, graphical processing units. Those are what are used to train things like neural networks because they optimize matrix multiplications. And they're able to handle many, many parameters being multiplied together. And that is why companies like NVIDIA and now other companies that make these GPUs, these processors, are worth so much because AI is exploding and we need these processors to do the training. Theoretically, you could also use a CPU, which is central processing unit. Those are on laptops, personal computers. Those, in order to train a model for that, like you can't have very many parameters, like very simple, maybe linear regression type of stuff. So mainly you need GPUs these days, and they are rapidly being developed. I think there's like 10,000 companies making chips to process machine learning models. One of the issues with GPUs is that they are expensive and there is a shortage of them. But as I said, many companies are making them more and more. Another way to speed up your processing is to have distributed training. So to be able to split up the models across different types of GPUs. So like you have, a set number of matrices on this GPU and a set over here, and you're able to like spread it all out and distribute the work across multiple like workers and then converge. So that's called parallelism. So the company that I am with called NativeLink is a company that is really good at this data parallelism and cloud compute. So it basically allows you to access GPUs on the cloud and send your data there and have it processed in parallel super, super efficiently. So I'll put a link. I did a 90-second explainer on NativeLink a couple days ago. So I'll put that there, and if you're interested, you can look it up. It's open source. It's a really cool project, and it's speeding up build times, which you will learn about, from like 15 minutes per person to seconds. So check that out if you're interested. But that's an example of data parallelism. So I talk about it a bit there. And if you have any questions on that, of course, feel free to leave a comment below. One thing I'm going to talk about for hardware are cloud platforms. So people can have their own GPUs, or you can connect to them remotely. So you can use your computer to kind of log in to a GPU machine that is somewhere else. And that is what they talk about when they talk about cloud platforms and compute on the cloud. It's just compute that isn't here. It's located somewhere else, but you can like log in from your computer and work on that as if like from your computer. So that's compute on the cloud. NativeLink, the company I work for, has cloud compute services. So if you don't have a GPU, you can use NativeLink's cloud, and usually you like pay per hour to use a cloud. Sometimes they make you do a month contract, but if you're just kind of trying things out, you pay usually per hour. I'm not sure how NativeLink prices its cloud just yet. I just started. It's exciting times, cool company. So something that we need to do when we are training a model is consider hyperparameters. So model parameters are different than hyperparameters. Model parameters are learned by the training data, and they include both the weights, which is, the input is multiplied by the weights. It goes through the layers, and then the weights are, in those layers, and then it finds the output. The biases are like, it's not multiplied, it just is added onto the end. So it's like WX, the weights, times the input is X, plus b. So rather than multiplying the input, you're just adding this additional matrix onto that multiplied matrix. It's just more parameters that help make the model perform better. It's just like, making the flesh of the model more performant so that it fits input to output better. It's just another type of parameter is the bias, but it's added as opposed to multiplied. The hyperparameters are values that you as an engineer set yourself. Some examples of hyperparameters are the learning rate. So remember we talked about gradient descent and reducing loss and how you find the direction to decrease loss and you just step that way. Your learning rate is how big of a step you take that way. And that's a very important hyperparameter. So this is an example of a learning rate that's too big, where you take a step towards the direction of the loss and you actually miss the minimum. And then there's an example of a learning rate that is too small, where it just takes forever to get there and you never end up really converging on the global minimum because you're just like barely moving towards a local minimum. And a local minimum is a minimum that's like near you. It's like the minimum in your kind of neighborhood. But if you were actually to expand your view to see more of the loss curve, you would see that there's actually a even smaller minimum. Another hyperparameter is batch size, so the number of samples in each batch. So the number of samples that are considered as the model makes an update to its parameters. Sometimes you want to increase the number of samples it looks at. Sometimes you want to decrease the number of samples it looks at. The regularization strength is how heavy you want to generalize. There are different types of hyperparameter tuning methods like grid search, which is where you look over a set number of values. So you decide like, oh, let's try, 0.25, 0.05, 0.005 for the learning rate. And then let's try, a batch size of 5 or 10 or 2. You set these values and then you just try every possible combination of them. You train models for each combination of those different hyperparameters. And then you find which model performs the best at, whatever iteration you decide. Because remember, you might do early stopping, which is what we talked about before. So that takes an engineer. They say hyperparameter tuning is often the difference between a good model and a great one. Some people argue that it really just matters about the data. So this is an argument that people have, but I do think hyperparameter tuning is important, as does my master's advisor and brilliant person, Michael Kuckendorfer. It's not just about the data, we think, but maybe it is. But I think there is some kind of tuning that needs to be done, but maybe not. That's why a lot of these like fine-tuning as a service models are difficult, because at least right now, a lot of models need like human intervention, like tweaking of these certain hyperparameters and changing things and whatever. So it's kind of just hard to just say, here are all the hyperparameters, here's the model architecture, pass in your data, and we'll have a model that performs well for you. At least that's the state of the union right now. So yeah, there isn't really a one-size-fits-all approach. The hyperparameters really depend on your problem and your data. So yeah, I had people coming to me last year saying like, oh, we're so excited, we're doing this fine-tuning as a service thing. And I was like, good luck. It doesn't really work that way right now. I don't know if it ever will, but maybe it will. Some tips are just start with a really coarse search of hyperparameters. So, do your grid search. Potentially, there's also like a random search where you do random values. I like to do grid search. Start with a really coarse, broad, choices to put into your grid search. So options for each of the hyperparameters, just kind of spread it out. And then you can refine over time as you find like, oh, this is, by a factor of 10 close to what I want for the hyperparameter tuning or whatever. And then you can zoom in as you want to refine the data, the model more and more. Okay, well, I hope this has been informative. It has been a lot. We talked about, the importance of training, how it works. We talked about gradient descent and loss functions. We talked about regularization and dealing with imbalanced data sets. We talked about transfer learning and its benefits and how it's kind of just how things are done today. We talked about hardware, distributed training, so parallelization. So just remember, model training is an iterative process. Do not expect to get it right on the first try. It takes time. But I hope that this overview has been helpful in understanding what the training process looks like, what is needed from AI engineers, machine learning engineers, actually, because you are working with the actual learning of the machine. So hope this is helpful to understand what machine learning engineers do. This is what I was doing. And next week, we will talk about training processes. So we'll talk a bit about different key terms, and that'll probably be a lot shorter of a video. But we'll probably recap what's going on this week, and maybe there'll be a Q&A, and I'll answer your questions that you leave in this video today. So make sure you go through and ask your questions because they're crucial. And if you have a question, that means I didn't explain something clearly enough. So let me know. And I am excited to have a community here. Someone commented that they think YouTube has a better community than, some other places, even like Reddit. I love that. I'm really interested in investing heavily in this community. So comment, let me know who you are. And I'm thinking of starting a Slack. So let me know if that's of interest to you as well. Anyway, hope this was helpful. Probably very long. I have to go through and edit this now, but I'll see you next week for whatever we have next Friday. Maybe it's day 5. And I'm just so glad that you're here. Please share this with your friends and like and subscribe if it's been helpful to you. And let me know in the comments also what you want to learn. Follow me on Instagram, on Twitter, on TikTok if that's your thing. And I'll see you soon. And thanks so much. This is Harper, and I will see you next week. Bye.